In this video, we shall discuss the most popular distribution of all. X is said to have the normal or Gaussian distribution written with the letter capital N with parameters mu and sigma square if X has density fx given by this 1 over square root of 2 pi sigma square. This sigma square is inside the square root. Then e to the power minus half x minus mu by sigma whole square for all x in R. The graph looks like this, which is often called a bell-shaped curve, much like the Cauchy distribution that we had seen earlier, except that the tails here are quite thin. They never touch the x-axis because it is e to the power minus something. It can never be exactly 0. The center, as you can very well guess from this, has to be at mu. And how much spread there is, that will be controlled by sigma. So if you change mu, if you increase mu, then your graph will move towards the right. If you decrease mu, it will move towards the left. The same shape, just translating left and right. Now if you keep mu fixed and if you decrease sigma, in that case the graph will look like this. So it will become more peaked. So this is for smaller sigma, this is for larger sigma, and here sigma always occurs as square. So we shall assume that sigma is positive and mu can be anything in R. Now just by looking at it, it may not be quite obvious why it is a density at all. We can say it is non-negative, but why should it integrate to 1? For that we shall need one result. The result is that gamma of half is square root of pi. We are not going to prove this result here, it's a fact from real analysis, but we shall be using it. Our aim is to show that the total integral of the normal mu sigma square density equals 1. So we have written this down, the constant is outside, and this is what we have to work with. Now this very form suggests that you are going to use a substitution u equal to x minus mu by sigma. Since sigma is positive, this keeps the two endpoints the same, minus infinity to infinity, and this nicely becomes. Now also observe that I have dx and downstairs I have a sigma because sigma square under the square root. So dx by sigma is simply du. All that remains here is the constant 1 by root 2 pi. So we have to show that this integral equals 1. Again we are going to use a substitution. This time I shall put a variable for u square by 2. But before that I just notice that this thing is symmetric around 0. So I might as well work with 0 to infinity and multiply this with 2. So now I am going to put u square by 2 equal to v. The endpoints remain still 0 and infinity. This things becomes e to the power minus v. In order to compute du, you observe that u here is positive. So you can get back u from v. So from this I get du dv is 1 by square root 2v. So I can write here dv by square root of 2v, and I already had outside a little cancellation, this with this, and I am left with 1 over root pi integral from 0 to infinity v to the power half minus 1. I had a root v downstairs, so it was v to the power minus half, which I have written as half minus 1, e to the power minus v times dv. Now this I quickly recognize as my gamma of half. Gamma of half is root pi, so the two root pi's cancel, and I am left with 1 as I wanted to get. Well, here is the first theorem, an extremely useful one. It says that if x is a normal mu sigma square random variable and I give you any two numbers a, b in R where the first one is non-zero, then ax plus b, that is you are scaling x by a and you are giving it a shift by an amount b, will again have a normal distribution and the parameters are a mu plus b. So mu transforms exactly the same way as x does, and this one translates a square sigma square. That's why we need a not equal to 0, otherwise this will become 0. The proof is absolutely trivial using the one-dimensional Jacobian formula, so you should try your hand at it. Now, many authors will drop this condition. They will say, well, I do not need this condition, but if I allow a equal to 0, I can easily see what the distribution is going to be. It is going to be just the constant b. So they will define the normal b comma 0 distribution. So this is just any real number, but this is 0. Here, of course, we cannot write down the density, which had sigma in the denominator, but we define it just by looking at it. It has to be the distribution degenerate at b. By degenerate at b, I mean a random variable which takes the value b with probability 1. So it is just actually a constant. So in this generalized sense, a normal distribution may have density when sigma is strictly positive. It may not have density, and that is called a singular distribution, singular normal distribution, where in this case it has got a PMF and the mass is 1 at this value. Now here is a useful corollary to this theorem. If x has normal mu sigma square distribution, mu can be any real number and sigma is strictly positive, then x minus mu by sigma will have normal 0, 1 distribution, and this is called the standard normal distribution. The next theorem says that if x has normal mu sigma square distribution, then this mu is the expected value of x and the sigma square is the variance of x. In order to prove this, it's a good idea to start with the standard normal 0 and 1. Expected value of x is given by this. Now you may rush to the conclusion that this has to be 0 because it's an odd function and you are integrating over a symmetric interval around 0. But beware, we had a pretty similar situation in case of Cauchy, and the warning that was applicable here is applicable here as well. Namely, you first need to argue that 1/2 of it, this thing is indeed a real number. That is, it is not infinite. Because this being an odd function, this half and the other half should be negative of each other, but if this happens to be infinite, then the entire thing will be infinity minus infinity, which is not 0. But in this case, you should first convince yourself, which is not very difficult, that this is a finite quantity. Hence, you can indeed say that this equals 0. Similarly, expected value of x squared, which by the way is equal to variance of x because expectation of x equals 0, is, and doing a little bit of manipulation, it's quite easy to show that this is indeed equal to 1. So the result is proved for mu equal to 0 and sigma square equal to 1. Now in order to come to general mu and sigma square, what you do is the following. You define y as x minus mu by sigma, and we have already seen that this has normal 0, 1 distribution. So we have already taken care of this. Hence we know that expected value of y is 0 and variance of y is 1. So just manipulate from this. X is mu plus sigma y. So when I want to find expected value of x, it is mu plus sigma times expected value of y, that is 0, so it is mu. When you want to compute variance, the added constant vanishes, so it is sigma squared times variance of y, which is sigma squared. The characteristic function of normal is very much like its density. If x follows normal 0, 1, then its characteristic function is given by e to the power minus t squared by 2, no constant here. Now the proof of this is, the strict proof of this is beyond the course because it requires complex integration, but there is a simple heuristics to arrive at it. The characteristic function by definition is expected value of e to the power itx. Well, it is this I which is causing the problem, so for the time being, let's pretend I am working with a real variable s, just a real number s. So it is this thing. Now the entire thing is e to the power something. Something is a quadratic in x, so by completing square, etc., some very elementary high school level algebraic jugglery, you can show that this will be equal to e to the power a squared by 2. Now we shall do the dubious step. We shall just put it in place of this s, but this entire argument was based on the fact that s is a real number, it is not a real number, but still if you put it, you will immediately get it whole squared, that will be minus t squared. Now this substitution is actually justified. Once you know certain results from complex analysis, you will be able to justify this substitution, but until then this just serves as a heuristic method. In this exercise, you are to use this theorem that we just stated to find the characteristic function of normal mu sigma squared. So you have to use that standard technique. From here you have to go to there and apply this result and come back to normal mu sigma squared.